So just a sec, I'll move this away. So the topic of today's talk is locally fair partitioning. This is joint work with my colleague Pankaj Agarwal and our grad students Shah Hanko and Erin Taylor. Most of these slides were made by the students, though any errors in the slides are on me. This work, part of this work appeared in AAAI this year. So the problem the general problem we are considering is called the redistricting problem. So in this, so at an abstract level, we have individuals located on a plane, and each individual is represented by a colored point, say red or blue, and this represents their political affiliation or who they are going to vote for. And red and blue represent the two political parties. And our goal is to partition these points or individuals into K regions, such that each region is roughly population balanced. And the regions are compact and contiguous. Each region gets a label that matches the color of the majority of the points in that region. So if you have a region where there are 70% individuals are red and 30% blue, then if you do majority voting and choose a representative for that region, that representative will be red. So each region is essentially, each region is assigned a representative who will represent them in, say, the parliament, and the political affiliation of the representative we will assume matches the majority color of the points in the region. So the concrete problem we'll consider is what is called fair districting. So think of an example like this, which has 6 blue individuals and 5 red individuals, and you could draw districts that look like this. But if you did this, then 2 of the regions will elect a red representative and 1 region will elect a blue representative. And in a sense, this way of drawing districts is manipulating the districting process so that the red can obtain an unfair advantage in the parliament. And gerrymandering is the general sort of term used to denote districting processes where people try to manipulate things or create districts which sort of give one party an advantage. So one metric one could use is what is called global fairness, which is you want the number of seats or the fraction of seats or regions that have a certain color to be roughly equal to the fraction of individuals of that color in the population. This seems like this is sort of an ideal goal. This is what we would like to achieve. If the US population is 70% red and 30% blue, then you want 70% of the House seats to be to have red representatives and 30% to have blue representatives. But the problem is instances like this, where you have red and blue roughly scattered uniformly, they're more blue than red, and regardless of how you draw the district boundaries, you will end up electing only blue representatives. So some problem. So on this example, they have 9 blue and 4 red points, but there are 3 blue districts and no red districts. And such instances are what is called natural. What is happening is what is called natural gerrymandering. I mean, there's no malice in this. It's just the instance looks like this. And these kind of instances preclude having global fairness. So instead, we use something called, we've introduced something called local fairness. And the main idea is that we say that a point or individual is happy with its region, with the region label, if the label matches its own color. So if I'm a red individual and the region I'm in elects a red representative, then I'm happy with the outcome. On the other hand, if the region elected a blue representative, then you could think that this red point is unhappy with the label of its region. Now, if there are many unhappy points which are close by, so think about this oval on this figure, where there are 3 red points, they are in blue districts, but they are close by to each other. Then these points could sort of what do you call deviate, and form their own region in which they are happy. So this oval could form its own region, and that region would get a red label. And so these red points are initially unhappy, and had they formed this new region, they would have been happy in that region. So in other words, they can deviate and form their own partition. So we say that a solution is locally fair if there are no such deviations. And this is related to the notion of core from cooperative game theory, which is due to Scarf from 1967, and it has been widely studied in economics and game theory. So a notion is not exactly the core, but it is very related to the core. So before going further, let me just mention some related work. The topic of fair districting and like addressing gerrymandering has recently received a lot of interest in the social choice and the computer science community more generally. So I'll present some related work. So there's a notion of fair clustering, which is to add a notion of fairness to the classic clay clustering problems. And there's been a whole bunch of work in this direction. So for example, there's fairness based on proportionality, and there's fairness notions where each cluster has a similar ratio of colors. So you think of points as being red and blue, and you want the clusters to have the same proportion of red and blue points. And then there is work in redistricting, where you want to simply partition a geographic area into population balanced compact regions without considering the colors of these of the points. So you just want, how do you construct compact regions, K compact regions, which are population balanced? And that itself is a challenging problem because it's NP hard. And so there have been various heuristics and approximation algorithms for that problem. The next thing people have considered is auditing. I mean, given a district, given a map that people actually draw, how do you argue in front of a court that this map is fair, or why is it unfair, right? And this also has received a lot of attention recently. There have been people in statistics and social choice who have worked on various notions of how to audit a map. So our focus is a bit different from all this work. What we want to do is a fairness, we want to do local fairness. So it's a fairness guarantee that's based on local neighborhoods of point, under the restriction that this partition has some nice geometric properties. Okay, so without further ado, what is the problem we are considering? So the input to the problem is a set of n points, which are colored red and blue on a plane. And we have a number sigma, which is the ideal population size of a region. And we have a parameter epsilon, which is how much you can deviate from this ideal population size. And a region is simply a contiguous set of points. We'll make this a bit precise later. I mean, it's still a bit imprecise. I'll make it precise later. And what you want to do is partition your point set into K regions. And each of these regions has to be balanced in the sense that the population of the region has to be within 1 minus epsilon times the ideal population size sigma, and 1 plus epsilon times the ideal population size sigma. And the label of a region is R if the majority of points in the region is red and blue otherwise. So this is sort of the input to the problem. And we say a point is happy if the region label matches its color. Right? So just keep this notation in mind. We say a group is beta deviating with respect to this partition pi that we have found. If this group is in a balanced region, so the number of points in the region is within 1 minus epsilon sigma and 1 plus epsilon sigma, and the number of unhappy points in this deviating region is at least beta times sigma, and these points are the majority in that region. And a partition is locally fair if it has no deviating groups. So as an example, I mean, here is a partition, and the blue points in the center along with the red point in the center form a balanced region. So it has a right size, but the blue points are the majority there. And they're at least beta sigma of those blue points. And so they can deviate. Okay, so here is another example. So the top and the bottom instances are exactly the same instance, but we have found two different partitionings. So on this instance, the number of points is 15 and our ideal region size is 4, and we have some deviation from that, and beta is 2/3. So ignore the parameters. I mean, but on the top instance, if you look at the region D, it forms a deviating group because it has 3 blue points and 2 red points, and the region is the right size, so it can deviate. On the other hand, if you look at the bottom partition, then it does not have any deviating group. So the first partition, pi1 prime, gets a color of red, pi2 prime gets a color of blue, pi3 prime gets a color of red, and pi4 prime gets a color of blue. So regardless of how you form a region D, the majority points in that region will be happy, so that region won't deviate. So here is a problem instance where like you have to, where the problem, where you're finding the right partitioning is non-trivial. If you find an arbitrary partitioning, it might look reasonable, but it might not be locally fair. So just to summarize our results, firstly, we'll consider the locally fair partitioning problem on a line, and we'll show that even this problem is non-trivial. So for our analytic results, we will use a line. Now on a line, a region is simply a contiguous set of points, so that's easy to define. And what we do is we characterize the epsilon and beta. So epsilon is the deviation from the ideal partition size, and beta is like the number of, or the fraction of unhappy points relative to the ideal region size that you need to form a deviating region. And so we'll characterize the epsilon and beta for which a locally fair solution always exists. But the characterization will be somewhat pessimistic in the sense that we want a characterization for all possible instances. And then what we subsequently do is a beyond worst case analysis. We'll circumvent the existential impossibility results when the input itself shows some mild clustering or segregation, that red points are closer to red points, blue points are closer to blue points. And finally, we'll show that like finding, given an instance, finding a locally fair partition, if it exists, can be done efficiently. Okay, so firstly, let's move to the problem of characterizing the existence of fair partitioning. And there, if you can plot epsilon and beta on a two-dimensional plot like this. So again, epsilon is the deviation from ideal region size in the partition that you construct, and beta is the sort of fraction relative to the ideal region size of unhappy points you need to form a deviating region. So below epsilon equals 0.2, there's a sharp threshold. So if beta is bigger than 1 minus epsilon, then regardless of the problem instance, there will be a locally fair partitioning of that instance. And if beta is less than 1 minus epsilon, then there will be an instance, there will be a problem instance for which there is no locally fair partitioning. Regardless of how you construct the partition, there will be some region that will deviate. So this threshold is sharp. And for epsilon between 0.2 and 1/3, again, the answer is no if beta is less than 1 minus epsilon. So there will be an instance for which there is no locally fair partitioning. On the other hand, if beta is bigger than 1 minus epsilon, then the answer is yes, provided that we restrict the deviating groups to have exactly sigma points. So the deviating groups can't have variable size. And there are some technical caveats that some of our results hold for large and only for large enough. Okay. So that is the summary of the existence result. So what we are showing is like a sharp threshold. And let me give some intuition behind these negative instances. So if beta is small relative to epsilon, then there will be instances where there is no locally fair partitioning, and the instances look like this. So what you do is you construct. So what you do is your input consists of alternating runs of red and blue points, and each run is of length exactly beta times sigma. Because our partition size cannot be that small, it cannot be like beta sigma, it has to be larger. So any partition must look like what is drawn in this figure. So it must include some points of the minority color, right? And since these partitions have to be contiguous, at some point we must create two consecutive parts with the same majority color. But that includes this big region which of the minority color, and now this region of the minority color can actually deviate. Right? So that is the intuition behind our negative instances. But the one thing is that these kind of instances are very sensitive to stuff being on a line, and they're not robust to perturbation. So what we do next is go beyond worst case instances. So we consider inputs where the points are clustered into large monochromatic intervals. And this kind of arises in reality. It's called Schelling segregation or sorting, where people tend to move to areas with like-minded people. So what we show is that so sigma is the ideal region size that we want if every monochromatic interval. So if you have if your input is runs of monochromatic intervals, if all these runs are of length at least 2 sigma, right, then there is a locally fair partitioning where a small fraction of the points are not in the correct sized regions. So most of the regions are of the correct size, but a small number of points are in like wrong size regions. So if you throw these points away, everything is good. Right? On the other hand, if your monochromatic runs are really long, so if your instance has long monochromatic runs, like 1 over epsilon times sigma, then there is always a locally fair partition. So the moral of the story is, if your input itself is sufficiently clustered, then it's easy to find locally fair partitioning. Next, we look at the computational question. So the previous results are all existential and worst case. So the computational question is, given a particular instance and parameters epsilon and beta, does a locally fair partition exist? And what we show is a dynamic programming algorithm that computes a fair solution or reports none exists in time that looks, that is polynomial in n and sigma. Sigma is less than n, so you can think of it as like either n raised to 4 or n raised to 5 time. And the idea is that if you look at any deviating region, it intersects at most 4 parts of a feasible partition. So that implies that your dynamic program only needs to keep track of the last 3 partition boundaries, or a last constant number of partition boundaries, and we exploit that fact in creating the dynamic program. So just to summarize, we introduced this new notion of local fairness to these partitioning or gerrymandering problems, and it provides a fairness guarantee when global fairness is precluded because of natural gerrymandering. And also it provides an interpretable notion of fairness that you can audit on any given map. Given a map, you can ask, okay, is there a deviating region or is there not? So that gives you an interpretable, explainable way of saying whether the map is fair or not. It's one possible explainable way. So this problem is, and what we have shown so far, and this was in our AAAI paper, is that this problem is non-trivial even on a line, and we sharply characterize the boundary between what is achievable and what is not. So if you want to extend this to the plane, our lower bounds or impossibility results directly extend to the plane because stuff on a line is also on a plane. In terms of upper bounds and what is possible, what we are currently doing, and this is not in our AAAI paper, is empirically studying the notion of local fairness on real world problems and real world maps. So let me just describe our empirical setup and our preliminary results. So we use the 2016 electoral map and the election outcomes for North Carolina. We run the recom Markov chain to generate 1,000 maps. This Markov chain is due to Ford, Duchin, and Solomon. So what this Markov chain will produce, it will produce compact, it will produce a map with 13 population balanced districts. And since we are generating 1,000 maps, that gives us, and each map has 13 districts, that gives us 13,000 maps, 13,000 districts. Okay, and it is known due to a recent result of Procaccia and Tucker-Foltz that this Markov chain actually is biased towards compact districts. So you can think of this as producing population balanced compact districts. Without looking at the colors of the points, whether they're red or blue, it just takes the population and partitions it. Right? And it's like sort of widely used in this gerrymandering area. So for each of these 1,000 maps, what we do is we use the 2016 election data of how people actually voted, And then we check for deviating regions using all the 13,000 districts as potential deviation. So we take one map, we take all the 13,000 districts that were found for these 1,000 maps. We take each of those districts and ask, is it a deviating, would it form a deviating district for this one map, right? So in that sense, for each map, we can check if they are deviating regions against these 13,000 districts, right? And we check for deviations with either simple majority, like a simple majority could deviate, or whether the deviation needs 55% majority, or whether the deviation needs 60% majority. So here is an example map that Recom finds. If you take all the 13,000 regions and check against this one map using the 2016 election data, it finds 3 deviating regions. And in yellow on the bottom map, I have shown one of the deviating regions. So the top map and the bottom map are exactly the same. The colors are different, but the regions are the same. This yellow region at the bottom is a deviating region for this top map. So here are some results. What we found is that only around 5% of the generated maps have no simple majority deviations. The rest of the maps have simple majority deviations. So you can view these 5% of the maps as, roughly speaking, perfectly locally fair, that you couldn't find a deviating region. So in these no deviation maps, if you look at the number of districts that would vote red and the number of districts that would vote blue, then the number of red districts would be either 7 out of the 13 or 8 out of the 13. Just to contrast, I mean, the 2016 map that was actually used, that was actually drawn and used, but it was thrown out by lower courts but reinstated by the Supreme Court, had 10 out of 13 districts that voted red. And what we find is that fewer deviating regions, maps with fewer deviating regions are actually correlated with having more balanced seat allocation in this sense. And one question one could ask is, does local fairness just mean that we are just packing all the red voters in one district and all the blue voters in another district so that everyone is happy, but these districts are not really competitive? It turns out that is not the case. So districts are not significantly more partisan in these locally fair maps than in a random map that Recom generates. So it's like around 58% red for a random map, or 58% majority for a random map if you look at a district in a random map, versus 59.7% majority in the remaining minority for a map with very few deviating regions. And we have obtained similar results, qualitatively similar results for Texas and Pennsylvania. So here is an example of a locally fair map. So on the left is a locally fair map with no deviating regions, and on the right is a map which has many deviating regions. There are 460 deviating regions with 60% majority out of the 13,000 regions we tested it against. And in fact, 1/4 of the precincts are unhappy and they trigger deviating regions. That's quite a bit. At the same time, I mean, if you step back, in both these maps, there are 8 regions that will vote red and 5 regions that will vote blue. So from a seat allocation perspective, these maps are comparable, right? So in terms of global fairness, these maps are comparable, but the left map is locally fair in our sense, whereas the right map is not. And this fair map is a bit more partisan. The regions are a bit more partisan, 60% versus the unfair map. So this is the kind of result that we obtain. So this leads to several next steps that we are currently considering. Firstly, can we audit for local fairness more systematically, like not just look against these 13,000 maps, but actually check if there's any deviating region at all. And it's an NP-hard problem to find a deviating region. So we are devising heuristics for it. And again, we can ask, okay, what is the robustness of such notions of local fairness to real world constraints on these partitions? You can't find arbitrary partitions sometimes. And also there's uncertainty in the data. I mean, is it robust to, like, if you take not just the 2016 elections, but the 2012 elections, 2020 elections, I mean, there's uncertainty in how people vote. Is it robust to that kind of stuff? And also, is there second order unfairness? Like, can we preserve, are these districts significantly less competitive? We find it is not, but can we systematically say that? And does it lead to actually packing minority votes in fewer districts and so on? And finally, I mean, once we have the empirical findings nailed down, can we come up with theoretical models and analysis in this 2-dimensional space that can explain these findings? So that's where we are, and thank you.
you very much. Let's unmute ourselves and give a round of applause. Okay, so there are a number of questions. Let me start with a more technical question that Ulla asked. What happens with majority ties? Is that allowed?
Actually, majority ties, we want a strict majority to deviate. So if it's tied, then we say both parties are happy, I think, at least in the current paper.
Okay. Nisar, do you want to ask a question?
Great talk, by the way. So this is a nice relaxation of the core where you ask that not every agent in the deviating collision is happier after than before, but only some gamma fraction of them are happier or some beta fraction. Do you know if this relaxation of the core is studied more broadly in other social choice contexts?
So there's this, of course, there's this transferable utility core, which would be a very big relaxation, right? Where you say that not everybody is happier, but if you transfer utility around, then people are happy.
Right. And similar to that, there is also this recent work on clustering, core-in clustering with average, measuring the average utility and the change in average utility. But these are, yeah, more, I mean, these require comparing the utilities of different agents, whereas your notion doesn't. So that's why I was quite interested.
No, that's a very good point. Not that I'm aware of.
Right. Thanks.
Okay. I think Bill's question was answered. Reshef asks, what if you want to minimize region uniformity? What do you mean, Reshef?
So I agree, it's a very nice talk, but I may somewhat disagree with the motivation, because the way it contextualized is that uniform regions are best. So like ideally, we would just like to slice the map into uniform or almost uniform regions. But in the context of political election, I think that's a horrible solution, because it means that the election doesn't mean anything. And in practice, the voter turnout will be very low, as it is in uniform regions. So I can take like the same solution concept, but say that, I want to do the opposite. So what if I want to have regions that are as close to balanced as possible to, let's say, to maximize turnout?
Yeah. So, I mean, though there is some intuition that this will tend to make regions less competitive, I mean, I don't think we can formally show it. I mean, it won't always find very uniform regions, because if there is some deviating region, then it has to handle it, right? I mean, so of course, there are instances where nothing can be done. And what we are saying is that on instances where nothing can be done, this will be some kind of proof that nothing can be done. But in our empirical thing, we are finding that the regions are not any less, they're slightly less competitive, but it's not as if it's just like finding 100-0 partisan regions. I mean, it's like 60% versus 58%. So it's not. So that's something we are worried about. And your question is good, that if there is some way of combining like minimizing discrepancy with local fairness, that would be cool. So what you're saying is that having more competitiveness corresponds to essentially minimizing discrepancy between these, finding regions where the discrepancy is small between red and blue. Right?
The question related to this, you compared your partisanness compared to a random map from that Markov chain. Is that a good benchmark on that for that?
Yeah,
metric?
so that random maps have been used in court cases to argue auditing. So that is the standard way by which, so if you have a certain seat allocation, you say, okay, here is the distribution of seat allocations produced by these random maps. In fact, they use the recom Markov chain there. So it seems fair in that sense. But at a high level, you're right that local fairness is in conflict with minimizing discrepancy, at least intuitively. And so it will be good to combine the two notions.
Exactly, you want to ask a question about parties?
Yeah, so at like a few years ago, I was looking at the same motivation where what if you have like a map and 60% blue, 40% red, but the voters are spread so uniformly that no matter how you district, 100% of the seats will go to blue. And from that motivation, I was looking at a different notion of a game between parties rather than a game between voters, where for each party, you say the utility of that party for a districting is the number of seats that the party wins in that districting. And then I was looking at this notion of proportionality, where, for example, if you have two parties, you can say the proportional fair share of each party is the average of the maximum number of seats it can win and the minimum number of seats it can win across all districtings. And I think Ariel also had a paper on this notion, but in a continuous domain. So do you have any thoughts on I mean, it basically addresses the same motivation, where if a party just cannot win any districts, then its proportional fair share would actually be 0. So giving it 0 seats would actually be proportionally fair. Do you have any thoughts on kind of addressing this problem via a game between voters versus a game between parties?
I mean, I don't have any intelligent thoughts off the top of my head. That's a nice idea, and we didn't quite think about it as a game between parties. I know areas like, I don't know if it was like both of your work, where you had this Wall Street Journal articles where one party draws a district, sends it over to the other side, and they draw a district, and this goes back and forth, right? We haven't compared with that kind of approach, and we don't even know how to. Actually, we could try comparing with that kind of approach. What happens on random maps, but we haven't. No.
Sounds good, thanks.
Okay, Peter has a question.
Yes, now I'm unmuted. I'm just wondering, I'm coming from a country where we don't have districts, so the problem doesn't arise. We have different problems. But I'm just wondering that a basic assumption in all this districting seems to be that your districts are based on geography. And what if you take completely different criteria? For example, you make a two-dimensional map where on one axis you take average income, and on the other map you take a degree of education. Then you also have scattered points on a two-dimensional grid, and you can try to carve up points like that. Has such thing ever been considered?
I mean, one could theoretically do it. Like you're saying that each individual is represented by features, so you have some high dimensional feature space, and you partition the high dimensional feature space instead of partitioning just based on geography. In the US, our problem is motivated by what happens in the US, but abstractly one could do that. It might lead to more sorting, right? Because if you put all individuals with high income and education and stuff into one part, they are likely going to be homogeneous in how they vote and so on. So it might exacerbate the problem of discrepancy, that it might be less competitive than if you did it based on geography.
Well, presumably the districts could become by nature more homogeneous anyhow.
Yeah. I don't know. That's an interesting question. If you have that kind of data, then that would be an interesting thing to check out. But I don't think anyone has, at least in the US, people have exclusively focused on geography. So I don't know about work in that direction.
Okay, now my solution is don't have districts, but that
yeah, that would be
that's
ideal,
your solutions.
Right? Yeah, that would be an ideal thing, but we're stuck with what we have.
Okay, thanks.
All right, I'll close the question period for now. We're now going into a 10-minute break where I put you into random breakout rooms where you can socialize with others, or you can choose to get yourself a coffee, something else, and then we'll reconvene in 10 minutes. Welcome back. It's time for our second talk, and our second talk will be given by Eric Neyman. He's a PhD student with Tim Roughgarden at Columbia, and he's been working on eliciting beliefs, forecasts, knowledge, and aggregating them. And I think that's also roughly the topic of today's talk.
Thanks, Dominic. Can people see my screen?
I can, yes.
Great. As Dominic said, I am Eric Neyman, and this is joint work with my advisor, Tim Roughgarden. Let's say that you're an economist and you want to estimate next year's GDP growth. So you look at 3 macroeconomic models. One tells you that there's going to be a 3.5% growth next year. Another says 1.5%. And a third expects the economy to shrink by 1%. And you want to aggregate these into an all things considered best guess. This is the problem of forecast aggregation, and it comes up all over the place in lots of different areas of science. And the question we want to ask is, which method should we use? You could pick an expert at random to trust, or you could take the average of all the forecasts. Or maybe if you have some sort of prior, you can just ignore the forecasts and go with the prior. Or you could do something more sophisticated. For example, something that works well empirically is something called extremeization, which is where you take the average and then move it away from the prior. And to foreshadow a little bit, one of our main results will be, as far as we know, the first rigorous theoretical justification for extremeization. But more generally, we are interested in asking which aggregation methods work well and under which circumstances. So I'll start by guiding you toward a formulation of our problem by giving a couple of examples. Then I will share some of our results with you. First, in the prior free setting, which is where the aggregator does not know the prior. And then in the known prior setting, which is when the aggregator does know the prior. Now, in order to answer the question, which aggregation method should we use, we need a framework for comparing aggregation methods. And in particular, we want our framework to look favorably on aggregation methods that do well in general across a broad range of possible setups. We will assume that our experts are Bayesian and are starting with a common prior. Then they will each receive some piece of private information, which we call their signal, and update their prior based on their signal. Now, the aggregator receives forecasts from all of the experts, but the aggregator knows nothing about the experts' actual signals or about these signals' underlying structure. And we will aim to assess an aggregation method based on its expected performance in the worst case. So to formalize this, we will use something called an information structure. So let's say that there are K experts, and we are interested in estimating a quantity that we will call Y. An information structure is a joint probability distribution P over each expert's signal, which we'll call sigma I, and the value of Y. Now, you can think of an information structure as essentially being a model of the correlation between the experts' signals. So as an example, you could consider experts whose signals are drawn IID from some distribution. Or you could have experts who all have the same draw from that distribution. And while the marginal distributions of each expert's signal is the same in these two cases, the actual joint probability distribution is very different. And so we say that these information structures are very different from each other. So here is our setting. First, an information structure is chosen. And then the experts' signals and the value of Y are drawn according to it. Then the experts compute the expected value of Y conditional on their signal and report it to the aggregator. So the aggregator receives a number from every expert and uses their aggregation strategy to combine the reports into a single number. And we penalize the aggregator by the squared distance between the number that they say and the correct answer, which is y. Now, our goal is to minimize the expected penalty, so the expected squared distance in the worst case. That is for an adversarially chosen information structure. And for this reason, this setup is called robust aggregation because we want it to be robust to worst case choices of the information structure. So what is the best that we could possibly hope for? So here's something that we might aspire to. We could try to be as good as someone who knows the information structure and also every single expert's signal. Clearly, there is no way for us to do better than that. And in fact, this utopian vision is not realizable. But we can try to see how close we can get to it. And then on the other hand, one thing that we should definitely try to beat is the prior, just reporting the expectation of y ignoring the signals. And by the way, even if the aggregator doesn't have access to the prior, they can easily get at least as good as the prior simply by choosing an arbitrary expert to trust. So our goal is essentially to maximize our algorithm's improvement over the prior as a fraction of the improvement of someone who knows all of the expert signals over the prior. And we call this the approximation ratio. So here the numerator is essentially the quality of our algorithm's estimate, which we call x. So how much better it is in terms of the expected squared loss compared to the prior. And then the denominator is how much better an estimate that takes into account all of the signals is compared to the prior. So the approximation ratio is 0 for the prior and 1 for this aggregator who knows all of the expert signals. And we are trying to get as close to 1 and as far from 0 as possible. And I just want to note that ultimately, this approximation ratio is a means to the end of figuring out which aggregation strategies work well under which circumstances. So unfortunately, without making any assumptions, it is impossible to beat an approximation ratio of 0. To see this, we present a particular example of an information structure, which we call the XOR information structure. In the XOR information structure, each expert receives an independent random bit, and y is equal to the XOR of these 2 bits. So notice that each expert always reports 0.5 to the aggregator. And this is because from each expert's perspective, the other expert's bit is either 0 or 1, and it's 50-50 which one it is. And so their estimate of y, the expected value of y, according to each expert, is going to be 0.5. But if you hear 0.5 from both experts, then there's nothing better that you can do to aggregate these numbers than just reporting the prior, which is 0.5. And so without any assumptions, you can't beat the prior. Now, intuitively, the thing that's going poorly with the XOR example is that there are complementarities between the expert's information. So in particular, each expert's individual signal is completely worthless, but the 2 expert signals together are worth a lot. So this motivates defining a quality function, which is a function of the subsets of all of the k experts. So the quality of the signals of a subset of experts is how much better those experts are in terms of the squared loss of an estimate that takes into account all of their signals compared to just saying the prior. And one natural property that you might want from your quality function is that it be a submodular set function on the subsets of the experts. And this condition was introduced by Yiling Chen and Bo Wagner, and they called it weak substitutes, which is the term that we will use for them. And if you don't know what submodular means, the details are not important, but you should think of it as there being diminishing marginal returns to learning extra signals. And so XOR is not weak substitutes. In fact, it's as far away as you could possibly get from weak substitutes. Now, under weak substitutes, it's not hard to show that simply picking a uniformly random expert to trust attains an approximation ratio of 1/k. And the question you might ask is it possible to do better than that? Now, unfortunately, the answer here again is no. And the way to see that is we are going to construct an information structure in which we think of the value y as a secret. And we are going to give shares of this secret to each of the k experts. And we're going to do this in a way such that for any r of the experts, for some r between 1 and k that we will choose, for any r of the experts, if they take all of their signals together, they can figure out y exactly. But any r minus 1 of the experts, if they pull their signals, they will have no clue what y is. And it's not obvious that this can be done, but in fact it can. It's called secret sharing, and it's a neat solution to a cryptography problem from the 70s. Now, in particular, we will create this sort of information structure for a uniformly random r between 1 and k. And what this is going to do is it's going to make it so that any L experts can figure out y if and only if r is less than or equal to L, which means that they will be able to figure out with probability L over k. This means that this signal quality function that we discussed is additive. And therefore, this information structure satisfies weak substitutes. On the other hand, the aggregator can only figure out y with probability 1/k, specifically whenever r is equal to 1. And so a 1/k approximation ratio is as well as you can hope to do. So here's what we know so far. Without any conditions on the information structure, the best approximation ratio you can hope for is 0. Now, under the weak substitutes condition, an approximation ratio of 1/k is trivially attainable. Right? You can choose a random expert to trust, but doing better than that is impossible. And so we can ask whether there is a way to naturally strengthen the weak substitutes condition that allows us to do better. And the answer is yes. Specifically, we introduce a notion that we call projective substitutes. Now, wrapping your head around the definition of projective substitutes takes a decent amount of thought. But I hope to convey the intuition behind this definition. So weak substitutes is essentially all about how well a subset of experts can approximate the correct value of y. Projective substitutes, on the other hand, consider something broader, which is how well a subset of experts A can approximate the belief of a subset of experts B. And what I mean by that is if all of the experts in A pooled their signals, how well could they predict the expectation of y conditioned of all of the signals of the experts in B? And specifically, projective substitute says that if the signal of some expert I is announced, the experts in A become better at predicting the belief of the experts in B. And it turns out that weak substitutes can be rephrased in a way such that this is a simple generalization. And in fact, projective substitutes implies weak substitutes, so it's strictly stronger. And you can think of this notion as capturing the spirit of diminishing marginal returns in a broader context. So specifically, if instead it were the case that A became worse at predicting B as a result of some signal being announced, then there's some sort of complementarity going on between B and the signal of this expert I that was announced. And I want to note that as you will see from our results, this projective substitutes notion by no means trivializes the aggregation problem. And in fact, there are many examples of information structures that satisfy projective substitutes. So does projective substitutes let us do better? The answer is yes. And in particular, it lets us do better simply by averaging all of the experts' forecasts. So averaging the experts' forecasts gives us an approximation ratio of roughly 1.866 over K, which is a significant improvement over the 1 over K bound for weak substitutes. And interestingly, we now have a separation between how well choosing a random expert does and how well averaging does. That is, averaging gets us a strictly larger approximation guarantee, which was not the case for weak substitutes. So here's the main idea of the proof. Under projective substitutes, it's the case that experts' forecasts can't both be similar to each other and far from the estimate that you would give if you knew all of the signals. And basically that's because if both of these were the case, then the signals would have to have some sort of complementarity structure. And so under projective substitutes, it must be the case that either the forecasts substantially improve upon the prior, or the experts' forecasts are different from each other. So in case A random forecast substantially outperforms the prior. And it turns out that averaging always outperforms a randomly chosen forecaster. And so what this means is that sort of by definition, averaging gets a pretty good approximation guarantee. On the other hand, if B is true, if the experts' forecasts are quite different from each other, then averaging substantially outperforms picking a random expert. Because essentially you filter out the noise that comes from the choice of random expert, which is large if the experts are far apart. And we know that picking a random expert gets us a 1 over K approximation. So in both cases, you beat 1 over K by a substantial amount. So now you can ask, is it possible to do better? For K equals 2, the answer is no. Our bound is exactly tight. In general, maybe it's possible to do better, but certainly not by much. In particular, we have a 2 over K approximation negative result compared to our 1.866 over K positive result. And again, the way that this negative result works is via a class of information structures such that the aggregator cannot do well on all of them. And the way this class works is each expert receives an independent signal drawn from a normal distribution with variance 1 and mean mu, which is unknown to the aggregator. And then y is the sum of these signals. So here's what we know so far. Weak substitutes lets you get a 1 over k approximation. And so I've indicated these values for k equals 2 through 7. And then projective substitutes lets you do considerably better than that. So that's the second column. And then we also have a negative result for projective substitutes, which is the third column. And there's a pretty small gap between the second and the third columns. So projective substitutes allows you to improve a lot over weak substitutes. Now, so far, we've been assuming that the aggregator doesn't know the prior. And really, our negative result, the 2 over k result, depends heavily on that. In particular, if the aggregator knew the prior, they could do perfectly on the class of information structures that I described. If the aggregator knew the prior, this could potentially help them a lot because they would know not just the expert's forecasts, but the direction in which they updated from the prior after receiving their signals. Now, in particular, it turns out that a sensible thing to do is to extremize, meaning to take the average of all of the experts' forecasts and then move that average away from the prior. Now, this might be a bit counterintuitive, so let me give you a motivation for this. Consider a coin with a random bias, so a random probability of coming up heads that's uniform between 0 and 1. And we are interested in the bias. So why is the bias of the coin? Now, 2 experts each see an independent flip of the coin. It turns out that if an expert sees heads, then the expert should say 2/3. So let's say that both experts say 2/3. Then they both flipped heads, which means that if the aggregator knew that they both flipped heads, the aggregator would have access to more information than either expert individually. And so the aggregator would want to say something larger than 2/3. In particular, in this example, they'd want to say 3/4. So each expert sort of moved from the prior of 1/2 to 2/3, but the aggregator would want to move further away. And basically what's going on here is that we want to not overcount the prior. So we can think of each expert forecast as some mixture of the prior and the expert's evidence. But when we aggregate, we want to only incorporate the prior once. So by extremizing, we are essentially reducing the weight of the prior to something more sensible. And it turns out that for the 2 over k negative result that I mentioned earlier, extremizing by a factor of k is exactly the right thing to do. Empirically, it turns out that extremization works much better than simply averaging without extremizing. Now, how might you want to extremize? The simplest thing that you might think to do is to linearly extremize, meaning to pick some extremization factor of d, and then move the average, make your forecast, make your aggregate by moving the average away from the prior by a factor of d. So if you set d equal to 1, you'll just return the average. And then for d larger than 1, that's when you're extremizing. So what is the best d to choose? And given that choice of d, can we beat what we got in the setting where we did not know the prior?
Eric, you're running out of time, so a couple minutes, please.
Yeah, sounds good. Sorry. Yeah. And it turns out that the answer is yes, specifically for d around 1.3 for k equals 2, and then it grows to about the square root of 3 for large k. And this gets you an approximation ratio of around 2.598 over k, which is substantially better than what we could even hope to get in the prior free setting. So what we have here is a separation between what we can get in the known prior setting by extremizing and the prior free setting. And then you might ask, is there something that a different method of extremization that works better than linear extremization? Because it turns out that linear extremization can only get you so far. We show that it can't do better than 4 over k. And one idea might be to use the variance of the experts' reports. The motivation here is essentially that the more the experts' evidence overlaps, the less it makes sense to extremize, and also the lower the variance of the forecasts. And so the lower the variance, maybe the less extremization is appropriate. So I think that going beyond linear extremization is an exciting direction for potential future work. And I'll close by mentioning a few other potential directions. One is we looked at projective substitutes. Maybe there are other natural definitions of substitutes or something else entirely, other conditions on the information structure. Maybe you want to give the aggregator more information than just the prior. Or you might want to look at other notions of error besides squared distance. So in particular, maybe KL divergence is a good metric if the experts are estimating probabilities. In all, I think that there are lots of potential directions for future work, and I'm excited to see what comes out of this. Thank you.
Thank you. If we have any questions, feel free to either make yourself known in the chat or raise your hand. I have a brief clarification question. The 1.866, is that tight for averaging? So is there an example where averaging can't do better than 1.866?
Oh, I do not think that we have shown that it's tight for averaging.
Okay, because it seems like there's a gap to the two, and it would seem surprising if there's something more natural than averaging that can close the gap. So my guess would be it goes in the other direction. As in averaging is probably the optimal thing to do.
I agree that averaging is probably the optimal thing to do. To me, this is obvious for k equals 2 and a bit less obvious for k larger than 2. Yeah.
Okay.
Franz Dietrich, I see you have a question.
Yeah, thank you very much. This is a fascinating paper, and I share absolutely your impression that we should go away from just taking the average of estimate.
Bill, do you want to? Oh, there we go again. You broke off for a minute. You broke off at the start.
Sorry for that. Could you hear anything?
The last thing I heard was I agree with you. You want to go away from just averaging.
Oh, fine. So let me know if you don't hear me. One remark is that I think it would be very interesting to look at a special case of your problem where the thing you want to estimate is the probability of some event, and then you are in opinion pooling theory. The measure for the error, which is in your case, I think the squared deviation, would lead you to the optimality of estimating the probability by, if you like, the correct condition probability of the event given all the signals that are scattered around the group and that are not accessible. And that's the whole point. We want to find an estimate out of the individual submissions without people submitting the signals. So that might be, but that might be an interesting application. And there is a sharp formula that exists for what is the best aggregate estimate of the probability given the submitted individual probabilities, but that formula requires knowing the prior. And what I found so interesting in your work is that you acknowledge the practical problem that we don't know the prior from which people started. And if you allow me another remark or maybe a question, because you might be more an expert than me in that, it seems to me that if you acknowledge the fact that we don't know the prior from which people started before they observed their own signals, then as a statistician, one would have two possibilities how to react to that. One is to do Bayesian statistics and to say, let's have a prior over possible priors, perhaps a uniform prior over possible priors. That's, I think, what you did in your coin toss examples, where the bias of the coin is uniformly distributed on the interval 0, 1. That is Bayesian statistics, if you like. Or you could go classical statistics and say that the true prior is an unknown parameter, but that parameter defines the, it completely parameterizes the sample space, if you like, the samples being what people report as an estimate. And then you can do classical statistics with that and estimate, make estimations based on those observed data from the people. Sorry for being so long.
Yeah, I agree that those are all interesting directions. Yeah, when you're dealing with probabilities, things get a bit interesting because suddenly you're in this bounded range between 0 and 1. And so, you know, for example, if you try to average and then extremize, you might end up outside of the interval. So like, it's a pretty different setting. And I think that KL divergence is perhaps a more natural metric to deal with that. But yeah, I think that there's a lot of interesting questions there. Yeah.
Thank you.
I see a question from Zwicker W.
Right. So I had a question. When I hear different weather forecasts for tomorrow, I assume part of the difference is that they're running different computer models for weather forecasting. And when if I assume a panel of geologists is advising an oil company on whether it's a good idea to bid on a certain plot of land, but there might be oil under it, I assume they actually have common signals, but they have different educations. Now, if I understand your work correctly, it doesn't take account of this kind of thing. It assumes that different experts that saw the same signal would have the same response. Is that correct?
Okay, so my answer to that is it's sort of philosophical, but what I would say is that maybe these experts saw the same signal, but you know, when you say that these geologists have had different educations or something, I'm counting that as part of their signals. So it's sort of like maybe they have a lot of information in common, but I'm sort of saying that everything that belongs to something that only a particular geologist knows rather than everyone counts as part of their signal.
Okay, thanks.
Franz, another question?
No.
Oh, good. Anyone else? Yeah, Peter.
Concerning the last issue about different educations for the expert, aren't those differences captured by the information model, which basically is a multi-dimensional probability distribution, having a different distribution over the signals for every expert?
Yeah, if I understood your question correctly, yeah, so I am considering the education as part of the signal. And so you can sort of think about it as philosophically as perhaps a problem. Yeah.
It's a difference of the signal, it's a difference of the probability of the signal, which is captured by your information model.
My understanding of Peter's point is that you are allowing different probabilities for each eye. And so the agents are treated, or the experts are treated asymmetrically anyways. And so things like their education can be encoded in there.
You're saying that if you want to give different weights for different experts when aggregating, or?
No, just that the expert interprets the same value of the signal in a different way, rather than receiving a different signal.
So I would be interested if there is a model that involves signal experts interpreting signals in different ways. But that's sort of not how I think of our model. I think of it as the experts are being Bayesian and are sort of correctly interpreting the evidence that they have and coming to a correct Bayesian posterior.
Okay, thank you.
Okay, thanks.
Good. Now let's talk about future seminars. Bill, you wanted to announce our rump session plans.
Yes, so we would like to shake things up a bit, and we have something different in mind for the near future. Possibly in April or May, the idea is we would organize an oldies but goodies rump session. This would consist of 5 to 8 shorter presentations fitting in the same time frame as normally. Here's the idea. Suppose you wrote a paper some time ago and you feel it never got the attention it deserved. I'm sure none of you are in that situation, but perhaps you suggested a new line of theory, and to your surprise, no one ever followed up on that. Or you suggested, hello? Or you suggested a practical method for the real world, but it was never actually considered. So this is an opportunity for you to revive that old paper and tell us what was so great about it. If you're interested, you should email me by a week from tomorrow, Friday, February 25th. And I'm going to be sending out an email later today with the details about what you might include in that email to me. And you should get that soon. Thanks.
Very good. And for next week's seminar, Ulla, do you want to say something?
Yes, I can. Next month's seminar.
Next month, oops.
Yes, I can announce. So we're going to have, it will be on the 10th of March. As usual, we have 2 speakers. Varut Sukompong, sorry, is one of them, and Stefan Napel is the other one. It will be a mix of fair division and committee voting, and I'm sure it's going to be wonderful, just as every time. So I'm looking forward to that.
Okay, great. Thank you all for coming. Thanks to our speakers for great talks. And we'll see each other in March.
Bye-bye.
Bye.